Tonight, we are going to break a promise that science fiction has been making for 100 years. The promise that one day we will simply step aboard a ship, reach the speed of light, and cross the galaxy the way we cross an ocean. The truth is stranger, and, I think, more beautiful. Long before you neared light speed, the journey itself would defeat you in a whole chain of ways. Some would end the mission before it ever left the ground. Some would tear the ship apart, where a single grain of dust arrives like a bomb. Some would kill the body outright, where empty space itself becomes radiation. And one would take away everyone you left behind, without ever touching you. None of it is waiting outside your window. It all lives safely inside the mathematics, which is the only place anyone has ever traveled this fast. So settle in, let the day loosen its grip, and let us find out, slowly and honestly, why the universe holds a speed limit and what it hands us in return. Hello, and welcome. I am glad you found your way here, wherever you are, in a dark bedroom, on a long night drive, or simply resting with your eyes closed while the world winds down. You can let the day go now. Nothing in the next few hours will ask anything of you. There is no test at the end. There is nothing you need to remember. If you drift off somewhere in the middle, that is not a failure. That is exactly what this is for. But before we take a step toward the stars, I want to set down a few rules. Because this channel is built on a single idea, a true story, told plainly, is more wonderful than any exaggeration. So let me tell you what kind of story tonight is, and what it is not. Here is the first thing. No human being has ever traveled anywhere close to the speed of light. The fastest people have ever moved were the astronauts of Apollo 10 in May of 1969, falling home at nearly 40,000 kilometers per hour. Enormous by human standards. Measured against light, it is less than 0.004%. So when I describe later what happens to a body at 99% of light speed, I am not telling you what anyone felt. I am telling you what the equations predict. Nothing tonight is a memory. Everything tonight is a forecast. Which raises a fair question. If no one has been there, how can anyone know? The answer begins in 1905, when a young clerk in the patent office in Bern, Switzerland, named Albert Einstein, published the special theory of relativity. It made claims that sounded absurd. That moving clocks run slow. That mass and energy are the same thing wearing two coats. That the speed of light is a fixed limit stitched into the structure of space and time. And for more than a century, people have tried to catch it being wrong. They have failed every time. In the accelerators at CERN, on the border of France and Switzerland, particles are pushed past 99.9% of light speed every day, and they behave exactly as Einstein said they would. The GPS satellites above your roof carry clocks that are set, by design, to tick at a slightly different rate than clocks on the ground, because relativity requires it. Leave those corrections out, and the position your phone reports would drift by something like 10 kilometers a day. This is not an untested idea waiting for its first confirmation. It has been checked and rechecked at speeds no spacecraft has ever touched. That is the ground we stand on tonight. Now, about the title that brought you here. It says traveling at light speed would destroy you before you arrive. and I want to keep that promise precisely. So let me tell you what it means. It does not mean a monster waits between the stars. It means something quieter. Take the ordinary, tested laws of physics, the same ones running your phone, and apply them carefully to a human being and a human ship moving at nearly the speed of light. And those ordinary laws produce extraordinary consequences. Some of them would end the mission before it ever launched. Some would destroy the ship in an instant. Some would kill the body. And one, the strangest, would leave the body in perfect health and take away the entire world it came home to. We will walk through each slowly, from the most familiar to the most haunting. And one last rule, the one I care about most. Everything important tonight comes from somewhere you can check. When I give you a number, it comes from real institutions and named scientists. From NASA and the European Space Agency. From the physicists who have actually sat down and calculated these things. Where the science is settled, I will say so. Where something is an estimate, or a proposal, or an open question, I will say that too, in the same breath, and near the end. When we allow ourselves a little wondering about what the speed limit might mean, I will mark that wondering clearly, so you always know which parts are measurement and which are simply a quiet mind. Looking up, you never have to take any of it on faith. That is the point. Everything here rests on work that thousands of careful people have already done, and left out in the open for anyone to examine. And all that is left for you tonight is to listen, and drift, and let one of the strangest true stories in physics unfold at the speed of falling asleep. So here is where we begin. Before we can understand why the journey defeats the traveler, we have to spend a little time with the speed itself. Not as a number on a page, but as something you can feel the size of. Let your shoulders soften, take one slow breath, and come stand beside the fastest thing there is. Here is the number, and then we will spend the rest of this chapter learning to feel it. In the vacuum of space, light travels 299,792 kilometers every second, about 186,000 miles. Each second, numbers that large slide off the mind. So let us give this one somewhere to live. Start with the second itself. 1 second, the time it takes to draw a slow breath in. In that single breath, a beam of light could circle the entire Earth 7.5 times. Not cross a country, not cross an ocean, circle the whole planet. Every city and sea and mountain range. 7.5 times over. Before you begin to breathe out. Now let that beam leave the Earth. And watch what happens. Because this is where the story turns. The instant light enters open space, the fastest thing in the universe begins to look slow. That reversal is the single most important feeling I want you to carry through tonight. Space does that, not by slowing the light, but simply by being as large as it is. Send the beam to the moon, the only other place people have ever stood. It arrives in 1.33 seconds. When the Apollo crews spoke with Houston, that pause lived inside every exchange. A second and a bit of silence woven into every question and answer. Because even radio, which is light, cannot cross that gap at once. The hesitation you hear in those old recordings is not nerves. It is distance, made audible. Send it to the sun. And now it flies for 8 minutes and 20 seconds. Which means something strange is true all day, every day. The sunlight on your face this afternoon left the sun more than 8 minutes ago. You have never once seen the sun as it is, only as it was. If it went dark this instant, your sky would stay bright and ordinary for 8 more minutes. Nothing above your roof is live. Everything up there is a recording, arriving late. And the farther away it is, the older the recording. Send the beam onward, past Mars and Jupiter and Saturn, all the way to Neptune, and it travels a little over 4 hours. This is why engineers flying probes in the outer solar system cannot steer in real time. A command to a spacecraft near Neptune takes 4 hours to arrive, and its reply takes 4 hours to return. Everything must be planned in advance and trusted. Light is the fastest messenger that can exist. And even light turns a conversation across our own solar system into a full working day. And now, the step that matters most. Leave the solar system entirely and aim the beam at the nearest star beyond our sun. A small red star called Proxima Centauri. 7 times. The beam that lapped the Earth 7 times in one breath now flies, without pause, for 4 years and 3 months. 4 years. Send it tonight, and it would still be traveling after 4 more winters. More than 1,000 more nights of sleep like this one. And that is the closest star there is. The nearest light on a street that holds, by current estimates, somewhere between 100 billion and 400 billion stars. In our galaxy alone. Here is the thought at the center of this chapter. We named this speed after light, and I think that name misleads us. It makes the speed sound like a property of a thing, the way we speak of the speed of a falcon or a train. It is not. And in the next chapter, we will see why the speed belongs to the universe itself and not to the light. But the numbers have already shown you the deeper point. We imagine the speed of light as the answer to our dreams of travel, the finish line that would finally make the galaxy small. And the first thing the arithmetic tells anyone is that even the finish line is slow. Even perfection needs 4 years to reach the nearest star. Whatever hope we have of crossing to other suns will have to be built inside that fact, not around it. So hold both truths together as you rest. In 1 second, 7.5 Earths. To the nearest star, 4 full years. The same speed describes both. Nothing changed but the size of the stage. And if the fastest possible thing needs 4 years for the shortest possible trip, a very reasonable question rises. The same one every science fiction story is built on. Fine. That is light's problem. We build faster machines every century. Surely the speed of light is only the current record, waiting for someone bold enough to break it. That question deserves a real answer. And the answer is one of the strangest discoveries in the history of science, found by people who were not looking for it. And it starts with a man in Denmark watching a moon of Jupiter run late. In 1676, a Danish astronomer named Ole Rømer was tracking the moons of Jupiter, and he noticed something odd. One moon, Io, slips into Jupiter's shadow on a schedule you can predict years ahead. But the schedule drifted. When Earth was moving away from Jupiter, the eclipses ran late. When Earth was approaching, they ran early. The moon had not changed. The distance had. Rømer realized the light carrying news of each eclipse needed time to cross the gap. And when the gap widened, the news arrived later. It was the first real evidence that light has a speed at all. That seeing is not instant. Before that, nearly everyone assumed light simply was. Everywhere, at once. Roma showed it was a traveler. And once something travels, you can ask how fast, and whether anything can go faster. For 2 centuries that looked like an engineering question. Then, in the 1860s, a Scottish physicist named James Clerk Maxwell wrote down the laws of electricity and magnetism, and something unexpected fell out of them. The equations predicted waves, ripples of electric and magnetic fields moving through space, and they specified exactly how fast those waves must go. The number that emerged was the speed of light, appearing uninvited. Inside equations about magnets and currents, light was an electromagnetic wave, and its speed was not a measured accident. It was written into the laws. And here the strangeness begins. Maxwell's equations state the speed plainly, but they never say speed relative to what. Every other speed in your life is relative to something. A car does 100 kilometers per hour relative to the road, and if you drive beside it at the same pace, it stands still next to you. That is how motion has always worked. So physicists assumed light must work the same way, and that if you chased a beam fast enough, it would slow down beside you. In 1887, in Cleveland, Ohio, 2 American scientists named Albert Michelson and Edward Morley built one of the most sensitive instruments of their century to test exactly that. The Earth orbits the Sun at about 30 kilometers per second. So light measured along Earth's motion should come out slightly different from light measured across it. The way swimming upstream differs from swimming across. Their instrument was easily precise enough to catch the difference. They measured, and measured again, through different seasons and directions. The difference was not there. The speed of light came out identical every way they looked, as if the Earth stood perfectly still. It was one of the most carefully confirmed failures in the history of science, and for almost 20 years it made no sense. Then, in 1905, Einstein resolved it, and I will state his answer as plainly as I can, because the whole night rests on this one sentence. The speed of light is the same for every observer, no matter how fast they move. Chase a beam at half the speed of light. Measure it, and you will still find it pulling away from you at the full speed of light, exactly as if you had never moved. This has been tested for over a century, and it has never once failed. You cannot gain on light, not because your engine is weak, but because gaining is not something the universe permits. How can that be? If I run toward you while you drive away, I close the gap. That is arithmetic, not opinion. Here is the answer, and it is the deepest idea of the night. So let it arrive slowly. Speed is just distance divided by time. If the speed of light must come out the same for everyone, and it does, then for people moving differently, distance and time themselves must differ. Your meter and your second are not everyone's meter and second. The universe holds the speed of light fixed and lets space and time bend instead. Moving clocks truly run slow. Moving lengths truly contract. These are not tricks of perception. They are what space and time actually do, and we will feel their full weight later, in the chapter where time becomes the strangest hazard of the whole voyage. So here is the reframing I most want to offer, because it corrects the misunderstanding almost everyone carries. The speed of light is not a record, because a record is a mark inside the rules. And this is one of the rules. Breaking the sound barrier was a triumph, because sound is just vibrating air. And air does not define time. But the speed of light is woven into what distance and duration mean. Asking to go faster than light is not like asking for a faster plane. It is like asking to stand north of the North Pole. The sentence sounds fine. The place it describes does not exist. There is one thing the rule does not forbid, though. It does not forbid approaching the limit. 90% of light speed. 99.9. All of it is allowed. In principle, by every law we know, the wall stands only at 100. So the dream survives. Just barely. In the narrow space below the limit. And the rest of tonight is about what it actually costs to live in that space. The first cost arrives long before any danger out in the dark. It is simply the fuel, and the brutal arithmetic of paying for it. Every journey begins with a price, and the place to start is not out among the stars, but at the ticket counter. Before dust, before radiation, before time itself gets involved. Most travelers are stopped by something entirely ordinary. Energy, the plain cost of moving. Feel that cost the way we felt the speed. When you toss a ball, your arm gives it energy. When a car reaches highway speed, it carries the energy of its burned fuel in its motion. Double the car's speed. And in everyday physics, you need 4 times the energy. The bill grows faster than the speed. That is, in the slow world, where relativity barely whispers. As you climb toward the speed of light, the bill stops growing politely and grows monstrously. Because one of the ways the limit defends itself is by charging more and more energy for less and less speed. Reaching half of light speed already costs an enormous amount. Reaching 99% costs many times more again. And the final step, from 99.9 and onward to 100, does not cost a large amount. It costs an unlimited amount. That is not an engineering wall. That is the door closing. Stay below the limit. Though, and the price is still almost beyond imagining. Here is one number, drawn from Einstein's own equation. Kept round because the roundness changes nothing. Take a small spacecraft, about the mass of a family car. 1 ton, no crew, no cargo, just the machine. Bring it to 99% of light speed. The energy it must carry comes out on the order of everything the entire human species uses in a year. Every power plant, every engine, every stove and light bulb on Earth, running for a year, poured into one object the size of a car. And if you want it to stop at the far end rather than tear through the destination like a bullet, you must spend that much again. That is the easy half. Because the energy has to be carried. And the carrying is where the real cruelty hides. A rocket moves by throwing mass backward. To go faster, you need more fuel. But fuel has weight. So you need fuel to push the fuel. And then fuel to push that. The equation describing this spiral was written in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky, working largely alone, decades before any rocket reached space. His equation says the fuel needed does not grow gently as your target speed rises. It grows exponentially. The NASA astronaut Don Pettit, who has lived on the International Space Station, wrote a well-known essay about this, and he called it The Tyranny of the Rocket Equation. Tyranny is the right word. To carry a few people to the moon, the Saturn V rocket stood over 110 meters tall, and almost all of that tower was fuel, burned in minutes, to move a small capsule at the very top, and the moon is 1 1/3 light seconds away. The nearest star is 4 1/4 light years. Chemical fuel, the kind every rocket in history has burned, is so weak for this task that the numbers stop meaning anything. Run Tsiolkovsky's equation for a chemical rocket aimed at even a modest fraction of light speed, and the fuel required comes out larger than the mass of the visible universe. That is not a figure of speech. That is what the arithmetic returns. So the dreamers move to stronger fuels. Nuclear fusion, the fire of the stars, is millions of times better per kilogram than chemistry. In the 1970s, members of the British Interplanetary Society designed a fusion starship on paper, a study called Project Daedalus. And even their optimistic craft needed tens of thousands of tons of rare fuel to push a small probe to about 12% of light speed, with no way to slow down at the far end. Beyond fusion lies the perfect fuel, antimatter, which turns all of its mass into energy, perfect and almost imaginary. According to CERN, all the world's laboratories combined have ever produced only nanograms of it, at a cost that makes it by far the most expensive substance humans have ever made. So this is where the first defeat of the night happens. And it is worth naming carefully, because nothing here explodes and no one here is harmed. This is not a death. It is the death of the departure. For a crewed ship, with shielding and supplies and living space, the price of a ticket to near light speed is not merely high. With any technology we possess, or can currently even design in detail, it is unpayable. Most journeys to the stars end right here, on the ground, in the accounting. But unpayable today is not the same as impossible forever. And the truth runs both ways. The energy exists. The sun pours more of it onto the earth in a single hour than our species uses in a year. The physics forbids nothing below the limit. What stands between us and the stars in this chapter is not a law of nature. It is the gap between what nature permits and what our machines can gather. And gaps like that have closed before. So let us do what physicists do when they want to see a problem clearly. Let us simply suppose it's solved. Suppose the tanks are full. The price is paid. The ship is real. And you are aboard. The engines light. And in that instant, the journey stops being about money and becomes about your body. Because the next barrier is not out in space. It is inside your own chest. Speed, by itself, cannot hurt you. That may sound strange to open a chapter about being destroyed, but it is one of the oldest truths in physics. And you are proving it right now. Resting there, breathing slowly. You are riding the Earth around the Sun at about 30 kilometers per second, more than 100 times faster than a passenger jet. You feel nothing, and you never have, because smooth, steady motion is invisible to the body. Einstein built his whole theory on that fact. If a ship were already gliding at 99% of light speed, engines off, you could pour a cup of tea aboard it. and it would pour exactly as it does in your kitchen. What hurts you is never speed. It is the change of speed, acceleration. And acceleration is where the human body, which we now have to bring aboard, shows how gently it was made. Your body was shaped by one steady pull, the weight of Earth, which pilots call 1G. Everything in you is tuned to it. Your heart lifts blood upward against exactly that pull. Ask for more, and the body cooperates for a while. At 2G, you feel doubled in weight. Heavy but fine. Around 4 or 5G, the heart begins losing its push toward the brain, and vision grays at the edges. Fighter pilots, in pressure suits that squeeze the legs to force blood upward, straining every muscle, can hold about 9G for a few seconds. And it is brutal work. In the 1950s, a United States Air Force flight surgeon named John Stapp rode rocket sleds down a desert track in New Mexico to find the true edge. In December of 1954, during braking, he endured, for a fraction of a second, more than 46G and survived, barely, carrying injuries the rest of his life. His data still underlies crash safety today. So there is the map: 1G forever, 9G for moments, 46G once. At the brink, for less than a second, now set that fragile map beside the trip we are attempting. To reach near light speed quickly, in the hours or days that films imagine. The acceleration would be thousands of G. There is no suit for that. No training. No brace position. At those levels, the body does not injure. It fails completely. Everywhere at once. In the first instant, this is the immediate death, the one that ends the crew before the stars have moved at all. The films survive this moment by inventing machines that cancel inertia. We have no such machine, because physics offers none. But this barrier, unlike the last, has a door in it, and the door is lovely. There is one acceleration the body does not merely tolerate, but was built for. 1G, the Earth's own pull. And here is the trick, confirmed by relativity and by every astronaut who has floated in orbit. A ship accelerating steadily at 1G would feel, inside, exactly like standing on Earth. The floor would press your feet with your familiar weight. Tea would pour downward. You could sleep in a bed under a blanket while the ship gained 30 kilometers per second of speed every hour. Comfort and progress in the same motion. Keep that push up and simply never stop. And the mathematics is specific about what follows. After about a year of shipboard time, you would be moving at roughly 3/4 of the speed of light. After about a year and a half, you would pass 90%, and within 3 years or so, you would be beyond 99%, still walking around your cabin in ordinary Earth weight. The body is satisfied. The limit is respected. Nothing forbids it, except there is a tax. And it is easy to miss. The speed is allowed, but only at the body's gentle pace. And that pace costs years. Years of flawless engine burn. Years of fuel beyond anything the last chapter could pay for. Added on before the real crossing even begins. The limit is defended the way deep water defends the ocean floor. You may descend, but only slowly, and the slowness is the price. So let us pay it. In imagination, the impossible tanks are full. The engine burns at exactly 1G. Smooth as a quiet room, 2 or 3 years pass aboard, and the ship now moves faster than any human object ever has. Most of the way to light itself, you are alive, comfortable, unhurried, and it is precisely here, inside this apparent safety, that the voyage turns genuinely dangerous, because everything until now came from our side of the problem. The money, the fuel, the crush of thrust, those were our limitations. From here on, the threats belong to space itself, and the first of them is almost embarrassing to say out loud. The first thing waiting for you out there is a speck of dust. Space between the stars is not perfectly empty. It is almost empty. And the word almost is going to do a great deal of work over the next 2 chapters. Drifting through the dark, scattered thinly across the light years, there is dust, not the soft grey dust of a shelf, but tiny grains of ice and carbon and rock, most of them far smaller than the width of a hair. They are the ash of dead stars and the crumbs of planet building, and they have drifted out there, unhurried, for billions of years. In all of human spaceflight so far, this dust has barely mattered. Our probes cross it slowly, and a slow speck is nothing. A tap on the hull. Some spacecraft have even caught such grains on purpose. In soft panels, the way you might catch a snowflake on a glove. Now bring your ship into the picture, cruising near the speed of light, and hold the one idea this whole chapter rests on. The energy of a collision does not grow in step with speed. It grows far faster. In everyday physics, 10 times the speed means 100 times the energy. And as you push toward light speed, relativity bends that curve upward even more steeply. This is the same rule that made the fuel bill impossible in the last chapter, wearing a darker face, because energy does not care whose account it sits in. The energy that was so ruinously expensive to give your ship is, from the dust grain's point of view, energy your ship now carries toward it. For free. And remember what relativity taught us. There is no difference between you moving and the grain sitting still, or the grain moving and you sitting still. From your window, you are at rest, and the universe is streaming past you at 99% of light speed. Every drifting grain on your path is no longer a snowflake. It is a bullet, arriving with the energy of your entire journey packed into a point. Let me make that concrete, with the kind of figures engineers actually work with. A grain far too small to see, about a millionth of a gram, meeting your ship at 99% of light speed, would arrive with the energy of well over 100 kilograms of high explosive, a larger speck, 1 milligram, just barely visible, balanced on a fingertip, would strike with the energy of more than 100 tons of TNT. And it would not burst against the hull the way a shell bursts against armor. At these speeds, matter stops behaving like matter. The grain would drive into the ship's skin like a needle of pure energy, flashing whatever it met, metal or water or bone, into plasma hotter than the surface of the sun, drilling a channel inward before the material could respond as a solid at all. This is not a nightmare invented for effect. It is a published problem, being worked on right now for a real mission. In 2016, an initiative called Breakthrough Starshot was announced, advised by physicists including Philip Lubin of the University of California, Santa Barbara, with the goal of sending gram-scale probes toward the Alpha Centauri system at about 20% of the speed of light. 20%. Far below tonight's imagined cruise. And even at that fraction, the project's own scientists named interstellar dust as one of its most serious threats. A study in the Astrophysical Journal in 2017, led by the astrophysicist Tim Hoang, calculated that grains along the way would steadily erode the probe's surfaces, and that a direct hit from a large enough grain, large here meaning a few thousandths of a millimeter, could destroy a probe outright. Their proposed defenses are modest and realistic. Make the craft tiny, so it barely presents a target. Fly it edge-on to the oncoming direction. Add a millimeter or two of shielding to the leading face, and accept the slow sandblasting of the small stuff. That is the state of the art. Not a force field, a thin coat of armor, and good odds for a craft the size of a postage stamp. Now scale that back up to a ship large enough to carry people, their air, their water, their years of food, crossing not at 20% but at 99%. The target is millions of times larger. The energy per grain is far higher again, and the trip lasts years. Through dust, no telescope can map, because nothing can see a speck of rock in the dark between the stars. You cannot dodge what you cannot see. And at these closing speeds, there would be no time to dodge, even if you could. So this is the third barrier, and the first that arrives as sudden violence. Somewhere on the road to another star, the statistics say, your path and a grain's path would cross. Hold the strange doubleness of it, though, before we drift on, because there is something almost tender underneath. The dust is not hostile. Nothing out there is hostile. Those grains are the same dust that, gathered over billions of years, built the earth beneath your bed. No one laid mines along your route. The deep is simply full of the seeds of worlds, and speed alone rewrote their meaning. At a crawl, the dust is a snowflake, near light speed. The same dust is a wall of fire. Nothing changed but you. And there is one more turn, which opens the next door, because dust is only half of that word almost. Suppose your engineers somehow solve the grains. Suppose the hull holds, and every speck along the way happens to miss. You are still not safe, because between the grains there is something finer, something that cannot miss, because it is everywhere at once. When scientists call space a vacuum, they are speaking in comparisons. Against the air in your room, space is emptier than any laboratory on Earth can manufacture. The air you are breathing packs something like 25 billion molecules into every cubic centimeter. Every thimble of room, in the space between the stars, by decades of astronomical measurement, that same thimble holds, on average, about one single atom. One, mostly hydrogen, the simplest and oldest atom there is, left from the first minutes of the universe. That is how empty the deep is, the emptiest thing there is, without being perfectly empty. And now watch, one more time, what speed does to meaning. Bring your ship through that thin mist at 99% of light speed. From your deck, you are standing still, and the universe flows past you. Every one of those lonely hydrogen atoms is now an incoming particle, striking at 99% of the speed of light. And physics has a name for fast-moving hydrogen. A hydrogen atom is a single proton wearing a single electron, and at these speeds, the electron is stripped away on contact, leaving the bare proton to drive deep. A stream of fast protons is not a mist. It is proton radiation, the same kind doctors focus into beams to burn away tumors, the same kind that makes the inside of a running particle accelerator a forbidden place. Your ship, simply by moving, turns the gentlest, emptiest medium in nature into a particle beam aimed permanently at its bow. This danger, unlike the dust, has been calculated for exactly our situation by a scientist whose day work is medical physics. In 2012, William Edelstein, a physicist at the Johns Hopkins University School of Medicine, presented calculations at a meeting of the American Physical Society addressing this very question. What would interstellar hydrogen do to a crew traveling near light speed? At speeds around 99%, his work found the oncoming protons would deliver a radiation dose far beyond anything a human body can survive, and deliver it almost at once. A few sieverts, absorbed quickly, is enough to kill a person. The dose here would be many times that, arriving faster than any warning. His conclusion was stark. The crew would be lost almost immediately, and the ship's electronics would not long outlive them. The thin hydrogen of space, harmless at every speed humans have ever traveled, becomes lethal purely because of how fast you move through it. It is worth pausing on how different this is from the dust. The dust was a lottery, a question of whether your number came up somewhere across 4 light years. You could imagine luck. There is no luck here. The hydrogen is everywhere, smooth and continuous. An ocean you swim through every second of the crossing. It cannot miss, because it is not aimed. It is simply present, the way water is present around a swimmer. The grain was a bullet. This is the sea, and there is a quieter cruelty underneath. The part that stays with me longest. Nothing in this chapter required anything unusual to exist. No storm, no burst from a dying star, no rare cloud along the route. This is calm space on an ordinary day. The plain background of the galaxy, the same atoms whose faint radio hum astronomers lovingly map to chart the shape of the Milky Way. At walking pace, at rocket pace, at any speed we have ever traveled. This hydrogen is so harmless, we forget it is there. There was never a wall built against fast travelers. Something more absolute was arranged instead. The traveler builds the wall, out of the journey itself. Your speed is the weapon. The emptiness only has to hold still. Now, if you have been following the shape of the problem, you can feel where the mind goes next, because it is where every engineer's mind goes. Very well. The deep is an ocean of radiation and the occasional artillery. Then we do what humans have always done at sea. We build a hull. We put something thick and heavy between the crew and the water. A great shield on the bow. And we hide behind it for 4 years. It is the obvious answer, the human answer, and it deserves a real hearing. So, in the next chapter, we will try, sincerely, to build that shield, and we will meet a defeat unlike any other tonight, because it does not wait out in the dark. It grows out of the shield itself. So let us build the shield, properly, with the seriousness it deserves, because this is the human answer to every hostile sea we have crossed. When the ocean was dangerous, we built hulls. When the sky was thin, we built cabins. When space was airless, we built suits. Surely the deep is only asking for the next hull. And engineers already know roughly what it would want to be. Against the sandblast of dust, a thick sacrificial plate on the bow. Layers that can vaporize and be renewed. Against the proton sea, plain mass. Meters of dense material, because radiation is stopped by matter. And the more matter, the more stopping. Water works. Metal works. Ice works. Pile it on the front of the ship like the blunt head of a whale, and let the crew live in its shadow. But you already know the name of the trap we just walked into, because we met it in Chapter 4. Mass. Everything aboard must be accelerated with the ship, and the fuel arithmetic of Tsiolkovsky does not care whether a ton is food or armor. Every ton of shielding demands its own mountain of fuel, and that fuel demands fuel, and the exponential spiral we escaped only by imagination returns. Heavier than before, a shield massive enough to tame the proton sea could easily outweigh the rest of the ship many times over. The ticket price, already unpayable, multiplies. Two jaws close on the same ship from opposite sides. The deep demands a heavy shield. The physics of propulsion punishes heaviness above all things. Neither jaw cares that the other exists, and it can be worse than heavy, because thick shielding hides an awkward secret that anyone designing for space knows well. When a fast proton slams into armor, it does not simply stop. It shatters the atoms it strikes, and the wreckage sprays onward as new particles. Neutrons and fragments and high-energy light. A spray physicists call secondary radiation. NASA has studied this for decades in the context of cosmic rays, and the finding is humbling. For certain materials, particle energy, and shield thicknesses. Armor that is thick but not thick enough can deliver a worse dose to the crew than no armor at all, because it turns clean, fast particles into a wider shower of slower, messier ones the body absorbs more readily. Shielding is not a dial you can safely turn up a little at a time. In some configurations, there is a valley in the middle of it, where more protection means more harm, and the safe far side of that valley sits at masses, the fuel arithmetic already ruled out. So, the engineers reach next for the elegant answer. If matter is too heavy, use fields. Charged particles curve in magnetic fields. The Earth itself survives the solar wind not by armor, but by its magnetic field, which sweeps charged particles around the planet like a river around a stone. Real research groups, including scientists at the Rutherford Appleton Laboratory in England, have studied small artificial magnetic shields for future crews. And for the slow speeds of today, the idea shows genuine promise. But scale it to our crossing, and the caution has to return. Bending, a particle arriving at 99% of light speed calls for field strengths and field sizes far beyond anything those studies contemplate, sustained for years by equipment with its own great mass, drawing on the same energy budget that was already impossible. And a magnetic field, however strong, is invisible to a neutral atom until it is ionized, and invisible to high-energy light always. The elegant answer thins the sea. It does not part it. There is one more idea, the most poetic. so let it have its moment. Some designs put the fuel itself out in front, or fly the ship behind a great shepherd mass, or, in the Daedalus study from the 1970s, spray a cloud of particles ahead of the craft to burn away dust before it arrives. Turn the voyage into a procession, the ship walking behind its own sacrifice. It is clever, and against dust it may truly help, but the proton sea flows through every cloud, and the cost of pushing a procession is the cost of pushing its total mass. And we are back at the start of the spiral. So look at the strange shape of this defeat. Nothing struck the ship in this chapter. This one is not an impact. It is a design that eats itself. Protection demand mass. Mass demand fuel. Fuel demand mass. And somewhere in that loop, the ship stops being a vehicle and becomes a monument. Too heavy to leave. Or it leaves light and unprotected. This is the only barrier tonight that we build ourselves. Willingly. Out of prudence. Out in the dark, the threats were dust and radiation. This one is drawn on our own blueprints. Still, the ship of our imagination sails on, because tonight we agreed to pay impossible prices to see the whole road. So suppose it all once more. Suppose the shield holds. The spiral is somehow broken. The crew rides safe behind their impossible armor. They have earned a quiet evening. Let them dim the cabin, drift to the forward window, and look out at the stars they are crossing toward. And here the voyage turns strange in a wholly new way. Because the view from that window is nothing like the view from yours. At 99% of light speed, the sky itself has been rebuilt. The stars have moved, and changed color, and gathered, and the light of the universe, the mildest thing in it, has begun to press back. Of everything I get to describe tonight, this is the one I would most love to see with my own eyes, and the one I am most glad I never will. What does the universe actually look like through the window of a ship moving at 99% of light speed? No one has ever looked, because no window has ever moved that fast. But relativity answers the question precisely, with the same tested equations that run the accelerators and correct the satellites, and physicists have used them to render the view. What they find is that the sky ahead stops being a ceiling and becomes a tunnel. Two things happen to light when you run toward it, and both are familiar to you from sound. The first, you have heard on any street. An ambulance racing toward you sings higher than the same siren racing away, because motion compresses the waves ahead and stretches the waves behind. Light does the same. Run toward a star and its waves compress, sliding its color toward blue. Physicists call it blue shift. The second effect rain can teach. Stand still in falling rain and it comes straight down. Run, and it seems to slant into your face, arriving from ahead. Light does this too. Motion tilts the incoming angles of the whole sky forward, so that stars truly beside you, even slightly behind you, appear shifted toward the point you are racing toward. Physicists call it aberration, and at everyday speeds you would never notice it. At 99% of light speed, it takes over the sky. So stand at the forward window, and here is what the equations say you would see. The stars have left their places. The constellations of your childhood have slid forward and crowded into a single bright patch dead ahead. A tightening ring of light around your direction of travel. while the sky beside and behind you empties into a widening dark. Physicists sometimes call this the headlight effect, and it does more than move the stars. It concentrates their light, gathering the glow of half the sky into a narrow forward cone, so the way ahead burns brighter than any real sky. And the colors have shifted. Stars near the center of the tunnel, their light compressed by your closing speed, have slid up the spectrum, orange turning white, white turning blue, the bluest sliding toward violet and beyond, up into the ultraviolet, where the eye cannot follow. At the edges of the bright patch, where the geometry is gentler, reddened stars linger like embers, a ring of embers, a core of violet fire, and behind you, spreading, the black. That is the true sky near light speed, not streaks and starlines, but a tunnel of gathered, sharpened light, and an abyss at your back. Hold the beauty, because it is real, and then let the physics finish the sentence without exaggeration. Blue shift is not really a change of color. Color is only what the eye makes of it. Blue shift is a change of energy. Every photon arriving from ahead strikes a little harder than it was emitted. And here I want to be more careful than a dramatic script usually is, because the exact size matters. At 99% of light speed, light coming straight at you is shifted upward by a factor of about 14. That is enough to push ordinary visible starlight into the ultraviolet and to carry the starlight that was already ultraviolet toward the soft edge of X-rays. It is not enough, at this speed, to turn the mild glow of the stars into a sheet of deadly gamma radiation. So, let me state the threat at its true size. As you approach light speed, the whole forward sky brightens and hardens, and its light climbs the spectrum, adding a real and rising burden to everything the proton sea is already doing to your bow. It is a genuine hazard, and it grows with every additional decimal of speed. But at 99%, it is the smaller partner in the radiation problem, not a separate instant death. Saying which dangers are the giants and which walk beside them is part of telling this story properly. And this one, at our cruising speed, walks beside. There is a deeper turn underneath it, though, and it is the reason this belongs in the night at all. Starlight is not the only light in the universe. In 1965, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, found a faint microwave hiss coming from every direction of the sky at once, and could not get rid of it, and slowly realized they had discovered the afterglow of the universe's own beginning. We call it the cosmic microwave background, and it fills every cubic centimeter of space, everywhere, with the mildest radiation in nature. Microwaves less than 3 degrees above absolute zero. It is also completely unavoidable, because it has no source you could steer around. It is the sky itself, glowing, and here the same rule waits. Patient at the top of the speedometer. Push close enough to light. Far closer than tonight's 99%. And blue shift goes to work even on the afterglow of creation. The whisper ahead warms, brightens, hardens. Push into the most extreme speeds the equations allow, and even that faint background would arrive as a wind of gamma rays. At our speed tonight, it stays a whisper, and I tell you about it not to frighten you, but for what it means. There is a final lamp woven into space itself that cannot be shaded, or dimmed, or dodged, and it waits only at speeds we cannot reach. So, the outside of the ship has now said nearly everything it has to say. The price, the thrust, the dust, the proton sea, the devouring shield, and the slow hardening of the sky. Barriers layered one behind another, and not one of them a monster, and every one of them something you could look up tomorrow if you wanted to. But the last barrier is different from all of these, and it is the one this whole night has been walking toward. It cannot be shielded against. Even in principle, it does not touch the ship at all. To meet it, we stop looking out the forward window. We turn, instead, and look back, toward a small blue world where the clocks have quietly refused to keep pace with ours. Everything we have met so far could, at least in a story, be beaten. Give the storytellers enough imaginary metal and imaginary energy, and the dust is stopped. The proton sea is parted. The burning sky is filtered to a soft glow. But the last barrier waits behind all of that, untouched, because it is not made of anything. It never strikes the hull. It does not need to. It was woven into the voyage at the moment the voyage was chosen, by the same equations that made the voyage possible at all. And it harms no cell in your body. It simply takes away the world you meant to return to. Begin with the fact itself. Stated plainly, moving clocks run slow, not appear to, not seem to. From some clever point of view, they run slow. We met the idea in Chapter 3, and I promised its full weight would arrive later. This is later, and I want you to know, before we go on, that this is among the most directly tested facts in all of physics. In October of 1971, two American scientists, Joseph Hafele and Richard Keating, did something wonderfully simple. They bought airline tickets for 4 atomic clocks. They flew those clocks around the world on ordinary commercial flights, once eastward, once westward, and then compared them with identical clocks that had stayed home at the United States Naval Observatory. Now, a flying clock is pulled in 2 directions at once. Its speed through space makes it run slow, exactly as we have been describing. But it also spends the trip several kilometers higher than the clocks on the ground. And Einstein's other great theory, the general theory, says that height alone makes a clock run a little fast. Which effect wins depends on how fast you fly and which way you go, because the Earth is turning underneath you, flying eastward, with the Earth's rotation. The clocks came home behind the ones that stayed, flying westward, against it. They came home slightly ahead. Both results, in both directions, matched what relativity had predicted before the planes left the ground, to within the precision of the instruments. The experiment has been repeated many times since, with far better clocks, and the answer never changes. Time is not a fixed backdrop. It is something motion and gravity both bend. In amounts you can calculate in advance and then go and measure. Our ship's speed is not an airliner's, at 99% of light speed. The equations say time aboard runs about 7 times slower than time on Earth. Push to 99.9, and the ratio climbs past 20. The nearer to light, the deeper the slowing, without limit. And here is the part the body cannot feel. and the mind can barely hold. Aboard the ship, nothing is strange. Your heart does not labor. Your thoughts do not stretch. Bread rises. Kettles boil. Sleep comes at night, exactly as at home. Time aboard does not feel slow, because it is not slow for you. It is your time, whole and ordinary. The slowing exists only in the comparison, in the silent gap between your clock and the clocks of home. Relativity never lets you catch it happening. It only lets you discover, afterward, what it has done. So let us work it through with real numbers. Take the nearest star, Proxima Centauri, and fly the most comfortable trip physics allows. Accelerate at a steady 1g for the first half. Then turn the ship and slow at 1g for the second half. So you arrive at rest, ready to stay. Run the equations, and the crossing takes a little under 6 years by the clocks of Earth, and about 3.5 years by the clocks aboard the ship. Your fastest moment, at the midpoint, is roughly 95% of light speed, not the deepest speeds we have imagined. Just the natural result of a steady push kept up across 4 light years, 3.5 years of your life, against a little under 6 of everyone else's. Arrive, and you are perhaps 2 years younger than the friends you left. And that already sounds like a gift. Travel farther, and the gift turns fantastic, because the gap widens without limit. Keep that same 1g going, and the mathematics is clear that a crew could cross the entire width of our galaxy, 100,000 light years, within a single human lifetime as they experience it. Hold that for a moment. One human being, one lifetime, the whole galaxy. Nothing in physics forbids it. Then turn the gift over, because the other face is engraved too. The galaxy crossing that cost the crew 1 lifetime cost the Earth 100,000 years. The short errand to Proxima costs the Earth 6 years, while costing you 3.5. Every hour of grace given to the traveller is taken, with perfect bookkeeping, from the world left behind. Fly far enough, and you do not merely leave home. You leave your era. The people who waved at the launch grow old on their own clocks, while you pass a single shipboard afternoon. Come back from a long enough voyage, and the children you kissed goodbye are elders, or names cut into stone, and the language has drifted, and the cities have changed their shapes, and every letter anyone promised to write has long since been written, and read, and filed away by people themselves now gone. Nothing malfunctioned. No one was harmed. Every clock, everywhere, told its own truth the whole time. That is what makes this barrier different in kind from all the rest. The others were failures of engineering. This one is the engineering, working perfectly. Scientists gave it a dry name, the twin paradox. From the thought of one twin who flies and one who stays. For a while, in the early 20th century, people argued it must be a flaw in the theory. It is not a flaw, and it is not really a paradox. The flying twin turns around, and that turning breaks the symmetry between them. And the mathematics agrees from every angle on who comes home younger. What it truly is, I think, is the universe's quietest toll gate. Every other price tonight was paid in energy, or mass, or shielding. This one is paid in belonging. The speed of light will let you go almost anywhere. If you can survive the road, it will not let you go and come home to the same world. Distance, at these scales, is not only space, distance is time, and crossing it spends the one currency no engine can mint. So this is the last of the barriers, and the only one with no wreckage and no flash. The traveler steps off the ship in perfect health, into a world where everyone they loved has finished their life, and the home they promised to return to has become a story other people tell. And if there is a mercy in it, let it be this. And rest here a moment before we go on. Nothing was stolen. The years of home were not destroyed. They were lived, fully, by the people who stayed. Under the same physics that carried the traveler outward, no one's world was taken away. The universe only refused, politely and absolutely, to pause anyone else's life while one person went to see the stars. Breathe there for a while. We have now walked the whole chain, from the counting house to the clocks. One door remains at the end of this long corridor. We have lived at 99% all evening. Why not 100? Why not the whole speed? The clean number the stories promised. The answer is the strangest arithmetic of the night, and it closes this half of the journey like a stone door, so that the gentler half can open. Every child who hears about the speed of light asks the same question, and it deserves respect rather than a pat on the head, because it is completely reasonable. If we can reach 99%, why not 100? What is 1 more percent? The car in the driveway does not strain any harder between 99 and 100 kilometers an hour. In the world that raised us, speed is a smooth road, and the last step is just a step. The answer is no. And the road to understanding why starts at the most famous equation of the modern age, the one you have seen on posters your whole life. Energy equals mass times the speed of light squared. Einstein published it in 1905, in a paper only a few pages long, and most people know it as the equation of the atomic age, the one that says a little mass holds a great deal of energy, but it points at something deeper than power plants. It says energy and mass are two names for one thing, which means energy is not weightless bookkeeping. It has heft, and that has a consequence for anything you try to push toward light speed. 1. The famous equation only hints at, and which the full mathematics of relativity spells out in detail. The energy you pour into the ship does not keep turning into speed at the same rate. As the ship approaches the speed of light, more and more of what you spend goes into the ship's momentum and its total energy, and less into actual velocity. You push just as hard, and the speedometer answers with smaller and smaller numbers. Let the numbers show you the curve. Reaching half of light speed costs a certain enormous amount of energy. Reaching 90% costs several times more. The step from 90 to 99 costs more than everything spent so far. The step from 99 to 99.9 costs several times more again. Each 9 you add to the decimal multiplies the whole bill, and the multiplying never softens. By the time you are writing 99.9999, you are spending, for each new 9, more than entire civilizations could gather, to gain a sliver of speed too small for any passenger to feel. And the final step, from all those 9s to a clean 100, does not return a large number. It returns infinity. Not infinity as poetry, but as the plain output of the arithmetic, the mathematics reporting that no amount of anything would be enough. No one legislated this limit. And that is the heart of the chapter. There is no barrier hanging in space with a sign on it. The wall is not ahead of the ship. It is in the arithmetic of motion itself. And physicists watch it stand in the most direct way imaginable. At CERN, beneath the border of France and Switzerland, the Large Hadron Collider pushes protons until they circle its ring at more than 99.99% of light speed. It is one of the most powerful machines our species has built. And when its engineers double the energy of a proton and double it again, the proton does not double its speed. Its speed creeps upward by decimals, while its energy and its momentum climb enormously. The proton does not become a heavier thing. Its own inner nature, what physicists call its mass, never changes at all. What changes is that the same push buys less and less speed the closer to light it already is. 7,000 times the energy it has at rest. And the proton is still, stubbornly, below the limit. Meanwhile, light itself crosses that line effortlessly, everywhere, every second. So the child's question has one last chapter, and it is the loveliest. Why is light allowed? Because a particle of light, a photon, has no mass at all. There is nothing in it for the steepening cost to grab, and for anything massless. The equations do not merely permit the speed of light. They require it. A photon cannot go any slower, just as you cannot go that fast. It is born at the full speed of the universe and knows no other pace. Here, I want to be careful, because there is a beautiful thing often said about light that goes a step too far. People say that for a photon, no time passes, that it experiences its whole journey in a single instant. It is a lovely image, and you can see where it comes from. Along the path, a beam of light takes. The quantity physicists call proper time does come out to exactly zero. But relativity does not actually allow us to sit in a photon's place and look out. There is no valid point of view that travels along with a beam of light. No clock that could ever ride it. So there is no sense in which light feels anything, or experiences a journey at all. What we can say, cleanly and truly, is this. The light now reaching your window from a star 4 years away took 4 years by our clocks to arrive. And along its own path, the interval it crossed measures out to nothing. Departure and arrival are, in that exact and limited sense, zero apart, not a lived instant, a distance in time that simply equals zero. Light does not experience the crossing. Light is the crossing. So the truth under the whole first half of tonight finally stands in full view. The speed of light was never a speed in the way we meant the word. It is the boundary between two kinds of existence. On one side, everything with mass, everything that can hold a heartbeat and a memory, given time, and therefore bounded by it. On the other side, the massless, the timeless carriers, paying for their perfect speed by never having a single moment to spend. No engine crosses that line, because the line is not on the road. It is in what things are. We spent 7 chapters learning how the journey defeats the traveler. The deeper finding is quieter. At a clean 100%. There is no physically possible state in which a traveler with mass could exist at all. The question the stories asked, what would it be like to travel at the speed of light, dissolves, because likeness and experience and the feeling of a journey all live on this side of the wall, with us, in time. Let that settle. And notice the night has changed beneath you while we climbed. The chain of barriers is complete. From the counting house to the clocks, to this final wall in the arithmetic. And not one of them was a monster. Every one of them was grounded in physics we can check. Even where the engineering around it remains uncertain, and probably will for a very long time. If the night ended here, it would end true, but incomplete, because out in the real world, on this slow, safe planet, there are people who know every number we have spoken better than I do, and who are, right now, still planning to go, not against the physics, but through the narrow gaps it leaves open. The dark half of the night is over, and the question changes now, from what stops us, to what we are actually doing about it. On the 12th of April, 2016, on the roof of a tower in New York City, a small group held a press conference that history may remember longer than most of what happened that year. The physicist Stephen Hawking was there. So was the internet investor Yuri Milner, who had committed $100 million of his own money. Together they announced a project called Breakthrough Starshot, and its goal sounded, at first hearing, indistinguishable from science fiction. Reach the Alpha Centauri system, the nearest stars there are, within a generation, not in some far century, within the lifetimes of people already alive. You have spent the whole first half of tonight in the dark, so your first instinct is probably the right one. You are waiting for the place where the dreamers collide with everything we have learned. And here is what I find moving about this project, and the reason it opens the gentler half of the night. There is no collision, because the engineers of Starshot read the same hard facts we did, and accepted every one of them, and then did something quietly brilliant. They went through our barriers one by one, and instead of fighting them, they built a plan that starves each barrier of whatever it feeds on. Watch how it works, because each choice answers a chapter of our night. The barriers of fuel and of the fragile body feed on mass and on the presence of a crew. So Starshot removes both. The spacecraft, called a starship, is not a ship at all. It is a wafer a few centimeters across, a gram or so in weight, carrying cameras, a processor, and a transmitter. The senses of a robotic explorer printed onto something like a large postage stamp. No crew, so no 1G limit. No air. No food. No return ticket. The tyranny of the rocket equation feeds on carried fuel. So the wafer carries none. It rides a light sail, a mirror-thin sheet a few meters wide, and the engine stays home on the ground. The plan calls for a vast array of lasers, combined into a single beam with a power on the order of 100 billion watts, held on the sail for only a few minutes. In those minutes, by the project's own concept studies, the little craft would reach an acceleration of thousands of g, the very figure that killed our crew in Chapter 5, and the wafer would not care, because silicon does not faint. When the beam shuts off, it is coasting at about 1/5 of the speed of light, and the crossing to Alpha Centauri takes roughly 20 years, with the news of arrival taking 4.25 more to reach home by radio. And the hazards of the deep, the dust and the proton sea, the advising scientists, including Philip Lubin, whose work on directed energy seeded the whole idea, and Theme Hong, whose dust calculations we met earlier, answered them with the same philosophy. You cannot armor a wafer, so make it small enough that the sky mostly misses it. Fly it edge on. Accept the sandblasting of the smallest grains. And, most tellingly of all, do not send one. Send a fleet. The plan imagines hundreds, eventually thousands of starships, launched one after another, priced someday like consumer electronics rather than like battleships. Some will die to dust. Some will simply fail. The mission succeeds if even a few survive to sail through the Alpha Centauri system with their cameras open and whisper their pictures back across 4 light years. The design does not defeat the barriers. It agrees to lose to them, many times over, and win anyway by sheer arithmetic. I said at the start of the night that the speed limit is less a wall than a filter. And here is the first proof. The filter does not stop travel. It stops travelers. Strip away everything human, everything heavy, everything alive, and the road opens. I owe you a clear accounting of Starshot itself. The project is real, funded, and publishing. But it is a research program, not a countdown. Its own leaders describe decades of work ahead. The 100 billion watt laser array does not exist. A sail that can survive that beam without vaporizing is still a materials problem being worked in laboratories. Holding the beam steady on a sail a few meters wide through Earth's shimmering air. Catching a signal from a gram of electronics across 40 trillion kilometers. Keeping a chip alive through 20 years of the proton sea with no repairs. Each of these is an open question, and the project says so plainly, nothing tonight should leave you thinking the wafers are on a launch pad. What is on solid ground is the physics. No step of the plan asks the universe for an exception. And after a night like ours, you know how rare and precious that sentence is. But look at what Starshot had to give up to earn it. Because the cost points to where we go next. It gave up us. No astronaut. No passenger. No human eye at the window we imagined 2 chapters ago. The first explorers of another star system, if this is the path that works, will be machines the size of your palm. And the human role will be to wait a full generation for a photograph. Perhaps that is how it should begin. Every ocean we ever crossed. We sent driftwood ahead of us first, but it leaves the older dream standing unanswered. The dream of actual breathing people going, and that dream has its own long tradition, older than Starshot, slower, and in its way, more human. If we cannot make the crossing short, some have always asked the opposite question. What if we stopped trying to be fast and simply refused to let the slowness win? Every plan we have met tonight, even the wildest, kept one assumption hidden inside it, that the journey should be short. Because human lives are short, and the crossing must fit inside one. Let go of that single assumption, and a whole family of designs unfolds. The slow roads, each one trading away speed to buy back survival, and each one paying for the trade in a currency stranger than fuel. The first slow road is the atomic one, and it has the odd distinction of being the only interstellar drive ever seriously engineered with real hardware in mind. In the late 1950s, at the dawn of the space age, the United States government funded a study called Project Orion, in which physicists, including Freeman Dyson and Theodore Taylor designed a ship that would fly by throwing nuclear bombs out behind itself and riding the blasts against a massive pusher plate mounted on shock absorbers. It sounds like madness. And the engineering was deadly serious. Chemical fuel fails the rocket equation by factors beyond counting. But a nuclear blast carries millions of times more energy per kilogram. And Orion's studies suggested a bomb-driven ship might reach a few % of light speed, which would put Alpha Centauri roughly a century and a half away. The project ended in the 1960s, partly with the treaty that banned nuclear detonations in space, and it despondent live on paper. In the fusion-power Daedalus study we met earlier and its modern successors, a few % of light speed appears to be roughly what known physics offers a large crewed vehicle, which means every remaining slow road has to answer one brutal question. If the crossing now takes longer than a human life, who exactly arrives? The oldest answer is the boldest. If the voyage takes centuries, then let it take generations. Build not a vehicle, but a world, a sealed habitat with farms and air and light. Launch it with a crew of hundreds or thousands, and accept, with open eyes, that the people who arrive will be the distant descendants of the people who left. No one aboard lives the whole journey. The ship itself is the traveler, and the crew is a river flowing through it. Engineers and ecologists have studied the idea seriously, and the physical challenges are immense. Closed ecosystems that cannot fail for centuries. Machines that must outlive their builders. Populations large enough to stay healthy. But the deeper challenge is not mechanical, and it is the one that makes this perhaps the most philosophically loaded machine ever proposed. Every person born aboard inherits a mission they never chose. The middle generations live and die entirely in transit, farmers of a garden between the stars, keepers of a promise made by ancestors to descendants, with no departure and no arrival inside their own lives. Whether that is a gift or a burden is not a question physics can answer. And I will leave it resting with you as exactly what it is. An open question about what one generation may ask of another. The second answer tries to erase the problem instead of inheriting it. If the journey is too long to live awake, then do not be awake. Hibernation has a real research history behind it. Medicine already cools patients during certain heart and brain surgeries, slowing the body's demands at the edge of survival for minutes and hours. The European Space Agency has funded studies on inducing a hibernation-like state in astronauts for missions to Mars. Drawing on the biology of hibernating animals, whose bodies somehow endure months of stillness without the muscle and bone loss that would ruin a human. Let me mark the boundary plainly. No human being has ever hibernated. Nothing close to a years-long sleep exists, even in outline. And the distance between hours of surgical cooling and centuries of interstellar stillness is not a gap of engineering detail. It is a gap of unknown biology. The sleeper ship is, for now, a beautiful hypothesis, but consider what it would offer if biology ever allowed it. The crossing would shrink, not in the universe's reckoning, but in the traveler's experience, which, as we learned 3 chapters ago, is the only reckoning a life is actually lived in. And that thought uncovers the strangest slow road of all, the one nobody designed, because the universe had already built it and we simply found it waiting. Go back to the comfortable 1G ship and look again at what time dilation did. On the crossing to Proxima, The steady push cost the crew 3.5 years, while costing Earth almost 6. Push harder and farther, and that exchange rate steepens without limit. The galaxy in a single lifetime, which means, and I find this the quietly astonishing sentence of the whole night. The universe already contains a kind of hibernation, and it is speed itself. The traveler does not sleep through the years. The years aboard are simply fewer. Relativity, the same law that wrote the final barrier of the dark half, turns out to be the only genuine shortcut in the entire building, and it charges the exact price we named. The time is not skipped, it is paid in full by the world left behind. So look at the map these roads have drawn, because they all arrive at the same crossroads. The atomic road delivers your descendants. The generation ship delivers a people who never chose to sail. The sleeper ship, if biology ever permits, delivers you into a future you slept past. And the relativistic road delivers you, awake and clear-eyed, into a future everyone else lived through at full length. Every road to the stars, without a single exception, asks the traveler to give up their own present. The universe will sell you distance, but the only coin it takes is your era. All of that, though, is paper and proposal and promise. There is a much simpler question waiting, and it is the one that keeps me honest whenever these ideas start to feel too easy. How fast, right now, tonight, can we actually go? Not in a study, in metal, in the dark, above your head. In September of 1977, a rocket lifted off from Cape Canaveral in Florida, carrying a machine about the size of a small car, wrapped in gold-colored foil, with a wide white dish for an ear. Its name was Voyager 1, and its makers gave it a mission measured in a handful of years. Fly past Jupiter, fly past Saturn, send home the pictures. It did all of that beautifully, and then it simply kept going. Because there is no braking in deep space and no reason to brake. Tonight, as you rest, that same machine is still out there, still running, farther from home than anything human hands have ever made. It has left the great bubble of the sun's wind entirely. In August of 2012, its instruments felt the particles around it change, and NASA later confirmed what the readings meant. Voyager 1 had crossed into interstellar space, the same deep we have spent all night imagining, and it is reporting from inside it. This minute, on a radio whisper that takes many hours to reach the Earth. I bring the Voyagers into the night for one reason, and it is not nostalgia. It is calibration. All evening we have thrown around fractions of the speed of light as if they were simply choices. 20%, 99%, 1G forever. So before the night makes its final turn, let us stand next to the real record and let it resize us. Voyager 1, among the fastest things our species has ever launched, is traveling at about 61,000 kilometers per hour. That is a staggering speed by every human measure, from Florida to Australia in a quarter of an hour. Set it against tonight's yardstick, and it comes to well under 1/100th of 1% of the speed of light. At that pace, the crossing to Proxima Centauri, the crossing we made in imagination in 3.5 shipboard years, would take on the order of 70,000 years. And here is the detail I find most humbling. Voyager is not even headed toward Proxima. It is simply headed out, in whatever direction its last planet flung it. According to NASA, some 40,000 years from now, it will drift within about 2 light-years of a small star called Gliese 445. And that distant pass is the closest thing to an arrival in its entire future. There is a newer record for pure speed, and it is worth naming and keeping current, because these numbers change. As of now, in 2026, the fastest object human beings have ever built is a spacecraft called the Parker Solar Probe. Launched in 2018 to study the Sun, using the Sun's own gravity on its closest passes, it reached, at the end of 2024, a speed of about 690,000 kilometers per hour. That is roughly 190 kilometers every second. Fast enough to cross the United States in under half a minute. And it is the fastest any machine of ours has ever moved. Measured against tonight's yardstick, it is a little over 0.06% of the speed of light. Our champion, our record holder, still rounds to nearly 0 on the scale of this night. That is not a criticism of the engineers who built a miracle. It is the plain size of the gap between the era we live in and the voyage we spent the night imagining. Sit with the voyagers a moment longer. Though, because they carry a lesson, the numbers alone miss. Nobody aboard, nothing alive, no 1G limit, no shield, no fear. The whole chain of barriers we walked tonight has almost nothing to say to a machine that's slow and that patient. Dust at Voyager's speed is a tap, not a bomb. The Proton C at Voyager's speed is a drizzle its builders barely had to think about. Time dilation at Voyager's speed is a rounding error on a rounding error. The probe slipped past the universe's entire layered defense by being exactly what the filter lets through. Slow, small, unhurried, and not alive. They will outlast their own voices. Their power comes from slowly decaying plutonium, and it fades a little every year. And sometime in the years ahead, the last signal will go quiet. But the machines themselves will not stop, silent and intact. They will keep drifting among the stars for millions of years, long after the civilization that made them has become whatever it is going to become. Each one carries a golden record of sounds and pictures of Earth, a gesture toward any finder, though the plain truth is that the emptiness makes any finding wildly unlikely. The record is less a message to aliens than a message to ourselves, about the kind of species we hoped we were on the day we sealed it and let it go. So the calibration leaves us in a strange, split place, and both halves are true at once. One half is humbling, measured against the speed of light. Our entire space age, every rocket and probe and triumph, amounts to standing up from the chair. The other half is the opposite of humbling. 2 machines from the 1970s are in interstellar space right now, still speaking, on technology older than most of the people listening tonight. The crossing we dream of is thousands of times beyond us, and the first steps of it are already behind us, already flying, already out there in the dark. Hold both without flinching, because an accurate picture of our place on this road needs them both, which brings the night, at last, to its turn. We have finished every account the journey demanded. The chain of barriers, the engineer's answer, the slow roads, the true speed of our era. And through all of it, one thread has been waiting, deliberately unpulled. 4 chapters ago, time itself was the final barrier, the thief of the traveler's whole world. Last chapter, that same physics flickered for a moment as something else. A shortcut, a strange mercy hidden in the equations. And I asked you to hold it and walk on. We are done walking on. It is time to turn and look directly at the strangest truth in the entire night. The thing that defeats the traveler, and the thing that could carry a single human life farther than any dream we have named, are not 2 things. They are one thing, wearing 2 faces. Let us go back, one last time, to the ship, the impossible one, the gentle one, burning at a steady 1G, so its floors press up against its passengers' feet with exactly the weight of home. All night, this ship has been our way of touching each danger in turn. Now let it be something else. Let it be the answer. Because inside its mathematics, confirmed by every clock ever flown and every particle ever raced, the universe keeps a promise so strange and so generous that I have saved it for the end of the night, the way you save the best thing on the plate. Here is the promise. Built slowly, distance by distance. Suppose the ship accelerates at 1G for the first half of a trip, then turns and slows at 1G for the second half, arriving gently, at rest, ready to stay. This is the most comfortable journey physics allows. Felt from inside as nothing but ordinary Earth weight the whole way. Run the equations of relativity for that flight plan, the same equations that priced every danger tonight, and ask one question: how much time passes for the people aboard? To Proxima Centauri, 4.25 light years. The answer is about 3.5 years of shipboard time. Long, but ordinary, the length of a degree. To the Pleiades, the little cluster of stars you can find on a winter night, more than 400 light years away, where every clock on Earth would run through 4 centuries. The shipboard answer is about 12 years, a childhood, to the center of our own galaxy, some 27,000 light years through more stars than you could count in 100 lifetimes. The shipboard answer is roughly 20 years, a career, and to the Andromeda Galaxy, the nearest great galaxy to ours, 2.5 million light years away, across an ocean of distance so wide that its light left home before our species existed. The shipboard mathematics returns a number I still cannot read without feeling the floor tilt. Under 30 years, a single working lifetime, door to door, from the Earth to another galaxy, at a comfortable 1G, without ever once breaking the universe's speed limit. I want to be perfectly clear about what those numbers are, and are not. They are the output of tested physics, the same time dilation confirmed by Haffley and Keating's flying clocks, and by every accelerator on Earth. They are also attached to a ship that cannot be built, whose fuel problem stands beyond any technology we can currently even design, and whose hull would have to survive everything the dark half of the night threw at it, at speeds where those dangers only grow. Nothing from the first half has been repealed. The numbers are not a plan, but they are not fiction either. They are what the universe itself would charge a traveler, in the traveler's own time, if the engineering were ever solved. And that changes the meaning of everything we walked through tonight. Because look at what just happened to the final barrier. 5 chapters ago, time dilation was the tragedy with no wreckage. The force that takes away the traveler's world. Turn it around. And it is the only reason the galaxy fits inside a human life at all. Without it, the crossing to Andromeda takes 2.5 million years for everyone. Everywhere. Full stop. And the stars beyond our little neighborhood are locked away from every living thing forever. With it, the deep opens. The very slowing of the traveler's clock that severs them from home is the mechanism that shrinks the crossing to a survivable size. The killer and the gift are the same physics, the same equation. And which one you meet depends only on which way you are facing when it arrives. Facing home, it is loss. Facing outward, it is the key. And this, at last, is the full shape of the idea I planted at the very start of the night and promised to keep. The speed of light is not a wall. A wall stops everyone. This is a filter. And now we can finally read what it says. Because we have traced every line of it. It says you may not have speed and home together. It says the galaxy is open. But only one way. Only forward in time. Only to those willing to trade their era for the distance. Every danger we met tonight enforces some clause of that same contract. The fuel bill and the shield spiral keep out the casual. The dust and the proton sea and the hardening sky keep out the fragile, and the patient clocks collect the final fare from anyone who makes it through. Payable, not in energy, but in belonging. The journey was never forbidden. The terms were simply set, written into the structure of space and time where no engineering can amend them, and the signature line left blank. Whether anyone, human or otherwise, has ever signed, we do not know, but consider, gently, how this reframes even the great silence overhead, the quiet sky that has offered us no confirmed voices, a galaxy crossable only by those who abandon their own worlds and their own times would be a strange place. Its travelers scattered not just across space, but across the ages. Each one a one-way emigrant into the future. I will mark that thought as exactly what it is. Wondering, not knowledge, but it points somewhere worth resting in for the night's last stretch. Because if the speed limit really is a filter and not a wall, then the final question is not whether we can break it. We cannot. The final question is what kind of universe writes terms like these, and whether, seen whole, they might be something other than cruel. Everything until now has been measurement, or engineering, or careful arithmetic, and I have told you at each step which was which. This chapter is different, and I want to say so plainly before it begins. What follows is not physics. It is a way of sitting with the physics. New experiment can test it, and you are free to set it down the moment it stops feeling true. Think of it as two people looking at the same finished puzzle in a quiet room, wondering aloud what the picture means. Here is the thought. All night we have called the speed of light a limit and reached for words of restriction. Walls, tolls, contracts, fares. But there is another way to hold the very same facts, and it starts with a simple question. What would the universe be like without the limit? Suppose distance cost nothing, and any place could reach any other instantly, for free. Our first instinct calls that paradise. The galaxy as one small neighborhood. but sit with it a moment longer. In the dark. And the picture complicates. A universe with no distance is a universe with no shelter. Whatever exists anywhere could be everywhere at once. Uninvited. Nothing young would get to grow up unobserved. Nothing fragile would get a quiet corner. In our actual universe, the speed of light does something we, who dream of crossing it, rarely pause to thank it for. It wraps every star in a moat of years. It ensures that whatever happens out there, however wonderful or terrible, cannot arrive here quickly, and that whatever we become cannot spill quickly onto anyone else. I want to be careful in exactly the way we agreed. The universe does not have intentions. As far as science can say, the speed of light was not chosen by anyone. It is simply a feature of the space-time we happen to live in. And calling it a mercy is a human reading of an inhuman fact. The way calling rain a blessing is a human reading of weather. But readings matter, because we live inside them, and this one fits, without strain, every hard fact the night has handed us. The same limit that isolates also protects. The same filter that keeps us from the stars keeps the stars, whatever they hold, from us. The same clause that charges travelers their era ensures that no empire and no mistake can sweep across the galaxy faster than the slow pace of light. And there is a gentler layer beneath even that, one that returns us to the sky above your own roof. Because the limit does one more thing. So constant, we forget it is the limit doing it. It fills the night with the past. Every star you have ever seen, you saw as it was, years or centuries or thousands of years ago, because the light needed that long to arrive. The night sky is not a window. It is an archive, the deepest one there is. Without the limit, the sky would show only a single present moment, and the whole history of the cosmos would be invisible. Everywhere. Always. With it, telescopes become time machines, and astronomers reading the faintest, oldest light are looking down through time, into chapters written billions of years before the Earth existed. The very delay that puts the stars out of reach is what makes them readable. I said early tonight that everything above your roof is a recording, arriving late, and it sounded then like a limitation. Hear it again now. The universe keeps its own memory, and the speed of light is how. So let me gather the wandering into one place and then let it go, as promised. Perhaps the limit is best understood not as the universe saying no, but as saying not yet, and not all at once, and not without cost, which is, after all, how nearly everything worth having has ever come to us. What it stops is hurry, and a cosmos that stops hurry is a cosmos where a small world like ours gets billions of quiet years to turn sunlight into forests, and forests into minds, and minds into questions like the ones we walked through tonight. We are not locked out of the universe. We are held at arm's length by something that can, if you choose to read it kindly, resemble care. That is a wondering, not a finding, but it is where the whole night, read one last time in a gentle light, seems to me to point. And with that, the questions are finished. There is one journey left tonight, the shortest in the whole story, and the only one you will actually make. It is the trip from here, wherever your thoughts have drifted among the stars, back down through the dark to the room you are lying in, and the bed that is holding you, and the sleep that has been waiting patiently at the end of the last chapter. Come back slowly. There is no hurry. Tonight, least of all, let the galaxy close behind you like a book with its place kept. And come down the easy way, past the silent probes, still faithfully falling outward, past the pale outer ice, past the moon, holding its second and a third of distance from home, down through the thin high air, to a roof, and a room, and you. Feel the room a moment, the weight of the blanket, the familiar shape of the pillow, the small sounds a home makes when it thinks no one is listening. After a whole night at 99% of the speed of light, I want to point out one true thing about this exact moment, and it is my favorite fact of the night, saved for last. Relative to your bed, to your room, to everyone you love sleeping nearby under this same roof, your speed right now is 0. Exactly 0. And after everything we have learned tonight, you know what an extraordinary thing that is to be able to say, because relativity taught us there is no such thing as absolute rest. No cosmic anchor, no universal parking brake. There is only rest relative to something. Rest is not really a state at all. It is a relationship. It is what you have with the things moving through the universe alongside you. The Earth carries you around the Sun at 30 kilometers a second, and the Sun carries the Earth around the galaxy at more than 200 kilometers a second, and none of it registers as motion for you, because everything you belong to is making the journey with you. That is what home is, in the deepest physical sense there is. Home is the set of things you are at rest with respect to. And now you can see what the travelers of our long night were really giving up, and why the last barrier cut deeper than all the rest. It was never about the years. It was about this. The 0. To leave at near light speed is to be at rest with respect to nothing. To trade away every shared journey for a single solitary one. And to stay is not to be left behind. It is to remain in motion, tremendous motion, with everyone and everything that matters to you. All of you falling together through the dark so smoothly that it feels like perfect stillness. Because togetherness is what stillness is. The speed limit, the filter, the whole long contract we read tonight. None of it asks anything of you here. You have already chosen, simply by being where you are. The one speed in the universe that costs nothing and takes nothing, the speed of rest. So let the night settle into its final shape. The one I hope stays with you after the details fade. And the details are allowed to fade. The stars are real, and they are far, and the distance is not a flaw in the universe. It is one of the walls that holds the whole thing up. Inside that distance, protected by it, small worlds get to be quiet, and long experiments get to run. And on at least one of them, on an ordinary evening, a person got to lie down in a warm bed and understand, without traveling anywhere at all, why the light takes 4 years to reach the nearest star, and what it would cost to follow, and why the following can wait. The galaxy is not going anywhere. It cannot be rushed, and it will hold every open question from tonight, patient and untroubled, for as long as we need it to. If tonight gave you something, a new way to see the sky, or just a slow road down into sleep, then it did what it was built to do, and I am glad we walked it together. There will be other nights, and other questions waiting in the dark, and we can walk through those the same way. But that is for another evening. For now, let the lights of the galaxy keep arriving while you sleep. Old light, patient light, 4 years, and 4 centuries, and 4 billion years on the road, finishing its long crossings against your window, asking nothing of you. Let it arrive without you tonight. You have somewhere better to be. You are at rest. In the full meaning of the word, with everything that is yours. Good night. Sleep slowly. There is no faster way to morning. And there does not need to be,